Hello, today we're going to continue talking about dilations and their connection to scale factors. So our objectives are students will be able to use the dilation theorem to show that a scale drawn constructed using the ratio and parallel methods have scale factors that is the same as the scale factor of the dilation, or prove an image is not a dilation. So summarize that we're going to make sure that you understand the dilation theorem, which is written right here, and we're going to make sure that you can use that to prove or disprove whether an image is a dilation. And some of the vocabulary that you're going to see regularly would be scale factor, dilation, theorem, parallel lines, corresponding angles, and ratio. And so our first little bit here will be the proof. So our discussion is, in a dilation theorem, if the dilation has a center at O and a scale factor of R, and we have the pre-image and the image, P and P prime, pre-image and image, Q and Q prime, then the segment image is the scale factor times the pre-image. And we've seen that fairly regularly throughout this extension of dilation, is that the scale factor adds the proportionality that we need. And so the addition to this is that dilation theorem allows us to look at the ratios of essentially what is the image over the pre-image, the image over the pre-image, and that equals the scale factor. So again, some of the things that we want to make sure we understand, the parts of the dilation would be a dilation with center O and a scale factor of R. You may want to reword some of these just to make sure you understand that this is the pre-image. This would be the result or the image, pre-image, and image. And then we're back to really honing in on this relationship that the resultant or the image is the product of the scale factor and the pre-image. The next little piece of this is this relationship here. Okay? And so as we go through this proof, recall from the quick write from class that to describe how the scale factors really impact the image. So you have R is equal to 1, R is greater than 1, and R is between 0 and 1. Those are the three cases that we've kind of looked at. And what we're going to do is look at the proof for it all. Okay. So as I flip this over, the premise is that we have a dilation with center at O and a scale factor of R that sends P to point P prime and Q. So just as a reminder, this is point O. Your image points P and Q are here and here. And so just by looking at this, I understand that R must be between 0 and 1 because it reduced. Okay? And I have to justify each thing that I'm doing, and so this is one of my givens. And I know that OP prime over OP and OQ compared to OQ prime should equal R, and that's really the definition of dilation. So definition of dilation just as a reminder, corresponding sides are in proportion okay. And so since they're in proportion, this kind of connects back to the side splitter theorem. So if you have a theorem, you can always reuse it. So this is by the triangle side splitter theorem, which basically told us that if I have sides in proportion, then the result of that should be parallel lines. Okay, and so now I know I have parallel lines. And so a dilation with center P and a scale factor of P to P prime sends point O to P prime and Q to R. So they're going to draw. And so now what they did, this is kind of interesting, is they recentered their point. So now I'm recentering the point here, and I'm looking at the fact that P to P prime should have a similar ratio to P to O. They basically just flipped the ratio, and therefore there should be another spot along PQ that does the same thing, and that point is what they're calling R. All right. And so this is a basic definition of dilation centered at P instead of O. So there's a little like vantage point, switching of the way you might think about the problem. And what that does is it establishes R. But same reasoning, if I have this ratio, then I must know that the sides are parallel. So we can go back to this side splitter. To prove that they're parallel, and then ultimately, and you can kind of see this from this image, I have two parallel lines, so I can basically state that this image right here is a parallelogram, and that's ultimately what they did. So by definition of parallelogram, we know we have one. Now you might be wondering exactly why is that important to prove? Like, what is the value in showing this is a parallelogram? Well, first we have parallel sides, but once we get those parallel sides, you should just know the opposite sides are congruent, opposite angles are congruent, diagonals bisect each other. There's all these properties that can be used once I have a parallelogram. And so the one that they did choose was opposite sides are congruent. So RQ is congruent to P prime, Q prime. And so the reasoning is opposite sides of parallelogram P R Q prime Q are equal in length. Okay. Continuing on, that allows me to set up a ratio, because if lines are parallel, remember, it kind of goes both ways. It was that if and only if line, which allows me to go two different ways. So if things are parallel, then I know they must be in proportion. So by the triangle side splitter theorem, we know that the segment P prime R splits the side of triangle POQ proportionally. And that's how we get that ratio. We can then substitute. So if you look back, you're going to see somewhere we have P prime over O. And so by substitution, I can replace the R here, which allows me to rewrite this. So multiplication property. Of equality. And then the final piece is now I can substitute in P prime Q prime is equal to R times PQ, which proves that theorem we were just working on. And theorems, remember, have to be proven. Okay? Lot to digest. Take a moment, summarize, think about it. Thank you for your time.